Hello. This video is to explain the differences between the different reaction mechanisms. I want to compare nucleophilic and electrophilic. I want to compare substitution and addition. I'm going to start off with nucleophilic substitution. The key part of this is to remember what philic means. Philic means like or is attracted to. So this is where the species that's being added is attracted to a nucleus. Now you can see here we've got a nucleophile. Now this nucleophile has a negative charge. That's not always necessary, but this is a lone pair of electrons. So what's that going to be attracted to? The starting point here is this. The fact that we've got a C attached to a Br. Well, this Br is obviously a halogen, so it's going to be more electronegative than the carbon. So the bromine will have a delta minus charge, and the carbon will have a delta plus charge. What that means now is that our lone pair on our nucleophile, in this case a hydroxy group, that lone pair will be attracted here to the carbon. Now, I suppose in theory that would form a bond there straight away, which I suppose it does. But there's no real intermediate in this case. Everything happens all in one step. So as this lone pair of electrons forms a bond with the carbon, the electrophilic, the thing which likes electrons, this highly electronegative bromine group, that takes the pair of electrons from that bond and takes them onto the bromine itself. What that then gives us is our carbon, which we already started off with. The OH is now attached, and the thing that's left over is the Br minus. Now, there will be a spectator ion involved in all this, which is probably going to be a group 1 metal, maybe something like Na+. Now, that is because the reagent that you add into this is sodium hydroxide, and you'll end up with sodium bromide. But as I said, the sodium will in this case be a spectator ion. I'm going to move on now, and I'm going to change this now. And instead of it being nucleophilic substitution, I'm now going to do number 2. I'm going to do electrophilic substitution. Now, electrophilic substitution, this is the thing that happens on benzene rings. So let's draw ourselves a benzene ring. So there's our benzene ring. Now, because this is electrophilic, then this is something which has to be attracted to electrons. Now, we've got a region of electron density in this ring here. We've got these delocalized electrons. So if we have something which is nice and electrophilic, I'm not going to go into how this group is made. You can look up how this species is made. But we're going to have NO2+. So we're going to be nitrating this benzene ring. So in this case, the nitronium ion, this thing here, is attracted to the ring. Yes, that's true. And normally when something's attracted to something, you draw the arrows going from it to the ring. But in chemistry, what's important is we only ever draw the arrow going from the region of electron density to the positive. So we have our region of electron density here, which is in the ring, and so the electrons are attracted to that nitronium ion. So in this case, what we get our benzene ring, this carbon here, it's very easy to forget that there's a hydrogen attached to that, but there is. And now the nitronium ion is attached to it as a nitrate group. Right? Now, what is no longer happening is that we haven't got this full region of electron density here. These delocalized electrons are no longer fully delocalized all around the ring. So they'll be delocalized to this carbon, this carbon, this carbon, and this carbon, but not this one, because this one has its full complement of 4 bonds. So the ring now is slightly it's fully electron deficient. So the ring now has a positive charge in it. This now, of course, is completely unstable. So this intermediate won't last for very long, but it will last. So this pair of electrons here forming the bond to the hydrogen collapses into the ring, and the hydrogen goes off as an H+. So we end up with, I'll draw it over here, we end up now back with our fully delocalized ring. The NO2 is attached to it, and then we've got our H+ coming off. So this now is electrophilic substitution. We've substituted something on the ring. There was a hydrogen here, as we can see from this, and we've substituted it with an NO2. But this is electrophilic because the NO2+, that is nitronium ion, has been attracted to the ring. We don't show the attraction going that way, though. We show the movement of the electrons, and the electrons have come from the region of electron density to the nitronium ion. The next one I'd like to have a look at, it's still going to be electrophilic. Number 3. And this time we're going to have electrophilic addition. So we're not substituting this time, we are adding to the, in this case, a carbon chain. Now for electrophilic addition to happen, we need a double bond. Simplest compound with a double bond is ethene. So I'll draw it like this so I've got plenty of space. So we've got a double bond here, which is a region of electron density. The thing that I'm going to have attacking it is HBr. Now, again, this bromine is far more electronegative than our hydrogen, so the bromine is going to be delta minus and our hydrogen is going to be delta plus. Now, again, this is a region of electron density, and this is something with a slight positive charge. So this will be attracted to this region here. However, we don't show it in that direction. We always show the movement of electrons. The electrons move from the region of high density to the hydrogen to form a bond. You can see that I've drawn it slightly before the hydrogen, showing that the bond is actually being made there. Some people draw it through the carbon to show that the bond is actually from the carbon to the hydrogen. Now, as this bond here forms with the hydrogen, the bromine, the electronegative bromine, takes both of the electrons from the bond here to form a bromide ion. So you end up, again, this time we have an intermediate again, and so this time we're going to have something that looks like this. So this carbon is the one that has the hydrogen. We now have this bromine is Br minus. Now, the important thing to notice on our intermediate is that this carbon is electron deficient. It's only got 3 bonds because the fourth bond that was formed here has been lost to form the full bond between this carbon and this hydrogen. So this pair of electrons here is now here. So this now has a full positive charge on its intermediate. This bromine has got a full outer octet, so it's important to show the pair of electrons that are actually going to be creating this bond. So the pair of electrons forms a bond there with the carbon. this is actually a carbocation. The old name was a carbonium ion, but we call this now a carbocation. I'll write that word down here. That's a carbocation. Please, guys, it's not carbocation. Carbocation. Right, so now we are left with something which looks like this. So the bromine and the hydrogen have been added to the ethene. You can see there's nothing left over. It's not like the other two reactions where there's an H plus or something like that. There's a Br minus, I think, in the first one left over. This is electrophilic addition. So we've added to this, and we've added to it by adding something positive at first. So it's attracted to electrons. Electrophilic addition. The final one in our mechanisms, and I'll cover this for the sake of completeness, number 4 will be our free radical substitution. Our free radical substitution starts off with making a very reactive species. In this one, we tend not to draw out the mechanisms with the curly arrows and everything in the same way as we do with the others. The equations are more important in this one. So we have 3 steps. Our initiation to start off with. Our initiation, and normally we would have a halogen, and that halogen can only really be chlorine, bromine or iodine. It doesn't really work with fluorine because fluorine, the bonds are too tight. So our Cl2 will form 2 chlorine free radicals. I've put them 2 separate ones. You could write 2Cl dot. Bear in mind this needs something to get it going, and in this case the energy comes from ultraviolet light, H mu. Some people write HF. That's our initiation step. The next steps are propagation steps. These are the steps which carry on the reaction. So in this case, I'll react it with methane for simplicity's sake. So this time a CH4 will react with a Cl dot and a chlorine free radical, and that will give us, now it's easy to just sort of say an H comes off and a Cl goes on, but we have to do it step by step. So that gives us a CH3 free radical. Some exam boards are quite picky on this. They are starting to let people do it like that. Yeah. Some exam boards like to see the dot on the carbon because that's where it would be. So just be a little bit careful on that. For the sake of completeness and making sure you're fully correct, put the dot on the C. And then that gives you HCl. This species is obviously highly reactive, and that now will continue the reaction by reacting with a Cl2, which will give us a CH3Cl plus another Cl dot. Now you can see from this that this reaction both uses Cl dots and makes Cl dots, chlorine free radicals. So the chlorine free radical in this case is a catalyst. Finally, we have our termination steps. Now, a termination step is anything which involves a combination of 2 free radicals. So the reverse of the first one is always allowed, always. If you're ever asked for a termination step and they haven't said don't use it, always put a reverse of the initiation. That's a valid termination step. We can have a CH3 dot plus a Cl dot, gives us a CH3Cl, and a CH3 dot plus a CH3 dot gives us C2 H6. So that's the fourth reaction. It is a substitution reaction because we are replacing one of the H's on our methane with a chlorine. Remember that in this one, the chlorine free radical is behaving as a catalyst because it's regenerated. And that's the name of the method. It's that's the name of the mechanism. It's a free radical. Yeah, so we're making free radicals, we've got our dots, and it's a substitution because we're doing a replacement. We are not adding anything on without taking something off. So those are our four mechanisms. We've got our nucleophilic substitution, we've got our electrophilic substitution, our electrophilic addition, and our free radical substitution. The only other one you need to know is elimination. The reason I've missed that one off is because the question yesterday came up about the difference between nucleophilic and electrophilic, and I've just put the free radical in there for the sake of completeness. Thank you very much. I will speak to you soon.